which means in infinitesimal isometry, the derivative basically gives you an infinitesimal diffeomorphism, as we'll see. And when that diffeomorphism doesn't change the metric, it's a symmetry. And the associated vector field is called a killing vector. And whenever you have a symmetry, as you are familiar with, you expect to get some conservation laws. And we'll see exactly how that goes in the case of curved space. And then those conservation laws will be crucial in allowing us to solve particle motion, find the geodesics in the Schwarzschild field. So that includes physically the two traditional first verifications of general relativity, which were, of course, the precession of the orbit of the Mercury and the bending of light by the sun. So if you treat light as idealized as a massless particle, which is what we'll do. So so I think Schutz doesn't actually deal with it, I guess, but Wald has it in an appendix. So appendix section C1 and C2 correspond to that, to what we're doing here. So as we saw, if you take start with the covariant derivative and dot it into some vector field, then you get what we called actually d by d tau. Well, if this was dx by d tau, we get this covariant derivative along a curve, or in a particular direction, and along a curve if this is the tangent vector to the curve. There's a different way to get to different. When you have a curve, or more precisely, when you have a whole set of curves, when you have a field, a vector field, so you have a whole set of curves filling up space-time or some region of space-time, then there's a different way to form a derivative, and that's known as the Lie derivative, and it depends on v, where v is now a vector field. So I'm emphasizing field to mean that it's not just enough to have one curve. Here you can just have, for the Lie derivative, for the derivative along a curve, covariant derivative, you just need one curve gamma. Here, and to which the v is tangent, but in this case, you need a whole congruence, as it's sometimes called, of curves. In other words, you need to have a vector at every point in space-time, or at least in some neighborhood of the point in space-time at which you want to form this derivative. So how does this work? So imagine that you have all these vector fields V. Imagine that this were the flow lines of a fluid. So this is now some sort of fictitious fluid. So in the time in which it's flowing is a fictitious time. It's not the physical time. The physical time is, of course, just one dimension in the four-dimensional space-time. But now imagine some fifth dimension, so to speak, or some proper time, whatever you like to call it, not meaning proper time in the sense of distance along these curves, but just some new time parameter, often called lambda, of course. And imagine that these were velocity vectors of the flow of some fluid. So this fluid would then carry along the points of the manifold. If you had, for example, a little vector sitting in the manifold, you could have its tail lies on one fluid line and its head lies on the other fluid line. And now if you just made them follow along in the parameter time that defines the flow, then you would get a new set of vectors, whatever they would do. The head going, maybe I should try and do red. So say it's flowing a little faster in this direction, the vector would be stretched out, and in general it will be what we call dragged along the vector field. So this, I don't want to call this V, do I? This I want to call some other W. So this red vector is W. The vector field that we're dragging along is V. This is V. And that would allow us to that'll allow us to compare vectors at different points by this dragging. In fact, if you imagined a vector field W already a second vector field present on the manifold, and you let it flow along, and you just sit at one point and watch what's coming past you, you'll see that vector W change. And the rate of change is basically the Lie derivative. So it's very much an analogy to the notion of parallel transport, how it's related to covariant derivative that we talked about before. If you want to form the covariant derivative of a vector field along some curve, you imagine dragging it back by the parallel transport and sitting and watching how it changes with time. And that rate of change is the covariant derivative. Here you do the same thing, but you drag it back by the action, by the vector field V itself. You don't use any metric or anything other than V. But as I said, you need the whole vector field V, not just a curve, in order to do this. So let's see what that means geometrically, and then using that, we'll be able to relate the two derivatives. That is, we'll be able to write a formula for the covariant derivative, for the Lie derivative of a vector field, or more generally a tensor field. And that formula will be written in terms of the covariant derivative, although you don't you can do that, but you don't actually need a metric to define this Lie derivative. That's crucial. So in fact, when we write the formula in terms of the covariant derivative, we'll get a formula that's actually, we'll get the same result no matter what metric we got the covariant derivative from. So anyway, so let's first see what is the meaning of, geometrical meaning of this Lie derivative, the derivative of a vector field W with respect to a vector field V. Okay, so we'll do this for vectors, and then of course once Lie derivative of scalars is as usual trivial. You just need to because it's just asking you to compare. It's just the directional derivative of that scalar field along V, which is V dotted into its gradient, which we've seen before. So the first non-trivial case is the vector field, and then of course once you've done the vector field, then you can get all the tensors as usual. Get the covectors and the tensors, just as we've seen before. So let's start at some point in the manifold P, draw sort of a little infinitesimal picture in the neighborhood of that point P. So I'll just write these epsilons. I could just say, think of V and W as infinitesimal, but just to emphasize it, I'll put epsilons here. So from P, the infinitesimal, this epsilon V, causes a displacement to an infinitesimally nearby point, which I'll call Q. And then we have the other vector whose Lie derivative we're taking. So I've called that W. So again, let's choose our epsilon. And it will bring us to some other point, which I've called R. But from R, now there's again, this is V as a vector field. So there's a vector everywhere. So I call that's another epsilon V. It's not, of course, the same V. It's the value of V at the point R. That'll bring us to a point S. And then similarly, from Q, I can move off by epsilon W, and that'll bring us to a point that I've called T. Okay. Now, what the derivative is doing, we want to remember what we're trying to do. We're differentiating the field W along the field V. So what that's asking us to do is to take W at P and compare it to W at Q. And we said we do that by drag. Of course, you cannot subtract two vector fields you cannot even compare, in some sense, two vectors at different points. So we have to move this vector, this epsilon w, this t minus q vector, over to p, so it's in the same tangent space. And the way we do it, as I said, is by the means of the vector field v itself. In this case, I think I'm going to do it the other way around. Well, so what we want to do is we want to compare this. I think I'll push that. I think what I'll actually do is, instead of pulling this one back, we'll push this one forward to first order. That's the same effect, and compare them at Q rather than comparing them at P. The difference between those two things is a higher order object, higher order thing. So it won't affect the definition of the Lie derivative. So we want to compare epsilon w at Q, which is equal to t minus q, right, with epsilon w at P, which is equal to r minus P. So as I said, we'll carry this one. We'll carry this over to Q. So we'll do the comparison in T, the tangent space, to M at Q. That's where I've drawn the. If I'd wanted to do it the other way, I would have drawn the figure slightly different. So this is the convenient way for this figure. So what is this r minus P? Goes under the action of V. Where does it get dragged to? Well, P gets dragged to Q, and R gets dragged to S. So it becomes S minus Q, right? That's the whole calculation. So make sure that I did it right. So now I want to take the difference of these two things. I want to subtract the one from the other, epsilon w at Q minus w at P. So if I subtract these, I get t minus Q minus S minus Q, which is T minus S, right? So that will be our definition of Lie derivative. The Lie derivative at V along V of W, and with an epsilon squared will equal T minus S. So it's somehow like it's the failure of these curves to mesh, as people say. The vector field defining W and the vector field defining V don't quite close. If you go a fixed parameter distance along W and then a fixed parameter distance along V, or you reverse the order, you go a fixed parameter distance along V and then equal parameter distance along W, you don't quite come to the same point. And that difference, that represents the Lie derivative, okay, which is T minus S or S minus, T minus S. But since it's second order in epsilon, we want to divide through by epsilons. If we want something finite, then we divide through by epsilon squared. And this is geometrically our definition of the Lie derivative. Okay. Yeah? No, no chart was needed because these are infinitesimal displacements in the manifold. So you see, these T and Q are points of the manifold, and P and R are also points of the manifold. So once the reason I can't directly, when I say that I take T minus Q, of course, there's no real meaning to subtracting points of a manifold. So you're right that in a sense, this expression, if we regard it as the difference of two things, would have to be the difference of two vectors, and that would be in a chart. But I'm using this as a kind of notation to mean the vector, the infinitesimal displacement from S to t. So if you remember, that's how we thought of vector in the first place. So given two infinitesimally nearby points of the manifold, and this is all an intuitive way of talking, of course. Given these two infinitesimally nearby points, we get actually a vector in the manifold. And I'm not being extremely careful here because you might say, is this vector, should it be regarded as in the tangent space at Q or in the tangent space at T? And I think I'll dodge that question and say I'm regarding it as in the tangent space at Q. Okay. But the idea is that this is all taking place in the manifold itself. So one thing that follows from this immediately is that Lie derivative of V along V of W, I mean, this picture, as you can see, is symmetric. If I reverse the role of V and W, the only thing that will happen is I'll reverse the role of S and T, and the sign will change. And so it follows immediately from this picture that the Lie derivative of V along W and the Lie derivative of W along V are the same except for a sign. And for that reason, or probably for that reason among others, it's often, a notation is often used, which we'll use, is to call this this sort of bracket notation. Commutator is another name for the Lie derivative of V of W along V. Okay. So now let's see if we can get a formula for, as I said, so that you can be more computational instead of having to always draw these pictures. Can we get a sort of explicit formula for this Lie derivative? And we could do this. As you see, this picture, all I used here were the vector fields V and W themselves. I haven't used the metric at any place. So that means I could write a formula without introducing the metric. I will in a second. But in order to do that, I would need a chart, because in order to write down partial derivatives and so on, I would need a chart. However, if I'm willing to introduce a metric, and since we do have a metric in general relativity, I can actually write this Lie derivative in terms of the covariant derivative, and then I don't need to refer to a chart. Yeah. Where did I use that? This thing, yeah. Oh. Well, it's just a notation at this point, but it could be taken literally also, if you go back to that other. Remember, there was one of the definitions of a vector field was a sort of what's the word? A derivation on the space of the scalar fields, on the algebra of the scalar fields. If we interpreted it like that, in other words, well, we'll see it in a second. I mean, we're coming to that in a second. But if what I put here is these gradient operators acting on the vector field, then we'll see that this is literally the Lie derivative, that the commutator of this literally gives this thing dotted into the gradient along. In other words, the commutator of the gradient operators along these two vector fields is the gradient operator along this, what we call the commutator, or the Lie derivative. But yeah, we'll get that in a second. In fact, we'll get to that instantly. So let me. Doesn't the relation imply some kind of anti-commutation relation? It is anti. This isn't this. If you read this as just some function of both V and W, then it's odd in V and W, right? So it's natural to compare it to a commutator, because this is, if we exchange V and W, this changes sign. If I were to put here a commutator, then I'd have some sort of bracket, some sort of operation, which didn't change sign when I exchanged V and W. So that would be better if that would go with a plus sign here. Okay. So now the thing I was just saying will prove that now. I claim that if we take if we commute the two gradient operators or directional derivatives associated with the vector fields v and w acting on a scalar, so it's important to have it act on a scalar. I don't know what this means when I try to act on a vector, for example, or a tensor. That's why we had to introduce the covariant derivative. But I claim that as long as we act on a scalar, take the gradient along a particular vector field, that just gives you back another scalar field, then we can act on it a second time, and then we can commute them. I claim that that equals VW A grad A acting on the scalar V, where this VW is, as I've already written here, means this. It's the Lie derivative. So in other words, it's the Lie derivative along V of W dotted into the gradient and acting on the scalar field. And this is true for an arbitrary scalar field. This will now, let's see if we can justify this from the picture. And if you want to go backwards, you could say, you could view all this as motivation and say that this is going to be the basic thing that we can use formally to define the Lie derivative. If you want a more computational definition of the Lie derivative. So let's look at the picture. So I have to do a little calculation. Right. So for shorthand, I'm going to write. Oh yeah. Instead of writing this, just to make the notation a little more transparent, I'll just write this as the gradient along. I'll just write the v as a subscript. So this just means the partial derivative or the gradient along the vector field v. So now, using that notation, what I'm asking for here is, and I'll put in the epsilon squared again so we can remind ourselves to think of them as infinitesimal. It's the gradient. What I'm asking is the commutator of grad v with grad w, or partial v with partial w. So let's first take them in one order and then take them in the second order and form the difference. So again, what is this thing? What is this difference? Well, this is by definition epsilon. So think of one of the epsilons going into the v here. This is asking us to compare the gradient of w at p with the gradient of w at p plus epsilon v, which is q. So this is actually asking us to compare epsilon times the gradient of w of phi minus epsilon times the gradient of w of phi. In one case at q, okay, and in the other case at p, right? So this is just the directional derivative of epsilon, this epsilon directional derivative along the v. Now I have to plug in what those things are. So by this same token, that'll be, so epsilon partial w of phi will be phi, well, where was that? Partial w of phi, we want to take it at q, so it'll be t, the value of phi at t minus the value of phi at q, right? So it's phi of t minus phi of q is the first term. And the second term will be the same thing at p, which is phi of r minus phi of p. If I did that right. So of course, now, okay, so that's that. Now we want to do the same thing with w and v interchanged. Again at p. If you run through the same thing, well, To exchange P and Q is just, to exchange V and W is just to exchange Q and R and S and T, and not change Q with R and S with T, blah, blah, and don't change anything else. So what is that? Phi of S minus phi of R minus phi, what was R? Was S plus phi P, change the sign. Basically, if you can see what's happened here, this thing is symmetric in Q and R. It's just minus phi of Q minus phi of R. So under anti-symmetrization in Q and R, it goes away. And phi of P doesn't change at all. So under anti-symmetrization, it goes away. And so the difference, which was precisely this V grad V grad W acting on phi times epsilon squared, that difference is equal to what's left over, which is phi of T minus phi of S. Right? I'm going to have to subtract this line from this line. Right? But phi of T minus phi of S is the same thing. So these are equal, right? This is equal to this. But phi of T minus phi of S is by definition the derivative of phi along this vector from S to T. And that vector from S to T was, somewhere we have it, epsilon squared, here it is. That was epsilon squared times the lead derivative of V, blah, 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 blah. So this is epsilon squared times the lead derivative of V with respect to W. That whole thing, partial A phi, right? I mean, nothing should be it should be all straightforward. So canceling out the epsilons, then we've proven the lemma. So a corollary to this, which we already saw geometrically, is the same conclusion that this is antisymmetric in V and W. So did I? Yeah, it's this thing again. We see it computationally. Now let's use this lemma to evaluate the lead derivative in terms of the covariant derivative. I shouldn't really say evaluated it, but just to get a formula for it in terms of the covariant derivative. Okay, so how do we do that? So when I wrote grad V of phi, remember, that was just by definition, VA gradient of phi. But this is, of course, nothing can stop me from regarding this as the covariant derivative. It doesn't matter what metric I put here, or even if I got this connection, this covariant derivative, not even from a metric, no matter where I got it. Because remember, we had a more general notion of covariant derivative. This is always true. Covariant derivative of scalar is just its gradient. And once I have that, then I can just plug into this formula here that's in the lemma and see what comes out. So let this act on phi, and I'll get using this symbol to mean anti-symmetrizing in V and W, I'll just get VA grad A. Why do I need to? WV grad B I want to make that act on phi, and then I want to anti-symmetrize in V and W. But this is, so let me just pull the, so this gradient can act, this gradient operator here can act either on W or it can go through. So I'll just get two terms, which will be VA grad A WV times grad V phi. And then the other term will be VA WV grad A grad V phi. Now I want to, now when I come to anti-symmetrize, of course, anti-symmetrizing in B and W is here the same thing as anti-symmetrizing on A and B, but we know that so now I'm using that this covariant derivative is torsion-free, so which it always is if it came from a metric. So let's assume it came from our metric. So this gives 0 now, because it's anti-symmetrized in A and B. And then what's left is just anti-symmetrizing this term on A and B. So it's just equal to VA grad B grad A WB minus VWA grad A BB. And that whole thing acting on grad B phi. Okay, but of course this grad B phi is also equal to, now it's just a scalar field, so I can write it as the gradient of phi without reference to the covariant derivative. And then you just compare this formula with this formula, and you see that we've computed the covariant derivative, the Lie derivative, Lie V of W. So the conclusion is that the Lie derivative of W with respect to V is exactly this combination, VA grad A W, if I put a V here, WV minus WA grad A B. Right. So that's the formula for the Lie derivative of a vector field. So as I said a couple of times, it looks like it depends on the choice of covariant derivative, but we saw that the definition didn't ever refer to the metric, so it must not really depend on the choice of covariant derivative. And of course it doesn't, and you can check that in different ways. You could, for example, use the fact, you could imagine that we change this covariant derivative for some other covariant derivative. So we change the metric to some other metric, and we use its covariant derivative. Then we saw that those two will differ by some tensor C, A, B, C. And if you plug that in and use the fact that the tensor is symmetric in its lower indices, because of the torsion-free character of the covariant derivative, you'll see that that correction tensor drops out. So in other words, if you take delta to some other delta bar, which is equal to sort of delta plus C, roughly, in the sense that we saw more precisely in the formula that gives you the covariant derivative with respect to one versus the other in terms of this tensor C, which had this index structure, remember. Then, and use its symmetry, you'll see immediately that it drops out. The other thing that we can do, therefore, well, suppose, since this really doesn't depend on the choice of metric, we might ask how it would look in a coordinate chart where we will not ever have to introduce a metric. And as you can guess, just from looking at this formula, it looks exactly the same. But now I have to use these concrete indices. So it'll be V alpha, partial alpha, W beta minus, the other thing where I switch V with W. Okay. So there's different ways of seeing that. Maybe the most straightforward is just go back and just repeat the same computation we just did, but do it in a coordinate chart. When then these gradients just become partial derivatives, and the algebra is exactly the same, and you get the same formula, but now these are partial derivatives, and these are now components. Or if you want to be tricky, you can, let me write this one out exactly, minus W alpha, partial alpha. Okay, so that's enough. If you want to be tricky, you could say, let me introduce a flat metric which is flat in the given coordinate system. So not the physical metric, but just some metric which looks like the Minkowski metric in the given coordinate system. Then with respect to that metric, covariant derivative is just partial derivative. And then this actually follows as a consequence of this. In a slightly more tricky way. But in any case, that's the expression for it in the chart. So that's what do I want to say? Oh yeah, one comment also is that if we go back to this picture again, as I mentioned just after drawing it, that you might this little thing that represents the Lie derivative of W with respect to V looks like a failure of these vector fields to mesh. So if it is zero, if VW equals 0, then we could say that means the integral curves of V and W, which is what I was basically drawing here. This is one of the integral curves of V. This is another integral curve of V, and so on. This is an integral curve of W. This is another one. So people say that they mesh in the case when it vanishes. So that parallelogram actually closes. So if we draw a set of integral curves like that, so this was, say, V, or W, I think this was, and then the other one would be, let's say, V. We're saying that they mesh like this. This obviously would remind you of what's going on in a coordinate system. And indeed, in a coordinate system, the integral curves do mesh. And so in a coordinate basis, or in other words, if V and W are basis vectors from some coordinate basis, then we have E alpha A, partial A, E beta B, partial B, acting on phi. But now this is a coordinate basis, so this just, remember from when we were talking about bases, this of course just means to take the partial derivative taking the gradient along the beta basis vector of that coordinate chart just means the partial derivative, so that becomes partial x alpha, partial x beta, acting on phi, and of course that's 0, just because you know that partial derivatives commute, which is something you have to prove once in your life, but no doubt you've seen it before. So it means that in a coordinate basis, these things are, well, so it means that this thing vanishes. E alpha A, E beta B equals 0. So this commutator meant the commutator of the gradient operator, the directional derivative. This just means Lie derivative. So here I just mean Lie derivative. So that's not for any basis, of course, but I did say a coordinate basis. That's one other comment. Now, oh, yeah. Oops. Oh, I see what happened. This wrote up while I wasn't looking, disappeared. Yeah. So we don't need. Okay. So we have a formula now. So let's discuss, just as we did for the covariant derivative, we sort of defined it in some particular, more or less concrete way, and then we found some general properties that it has that are useful, that are always that come up again and again, that are useful. And we also wrote formula for it to show how it acts on vectors, how it acts on covectors, how it acts on, and once we knew how it acts on vectors, we showed how it acts on covectors, how it acts on tensors, and so on. So we can just go through the same exercise here and say that, and find the same thing for the Lie derivative. Okay. So first of all, the general property that it shares with just the directional derivative. Well, I mean, the Lie derivative acting on a scalar is just directional derivative, and we know that that's a derivation. It shares that property even when we extend it to tensors. And if you like, it's by definition. I mean, we can take it to be part of the definition. Or if you go back to the geometrical picture, imagine dragging tensors and so on. You have to, of course, make the rule that when you drag a product of two tensors from one place to the other, a tensor product, when you drag a tensor product of two vectors from one place to another, that's the same as dragging the individual factors and then taking their tensor product. In other words, dragging should commute with tensor product. And then you'll get that it is a derivation. So but it's now a derivation on a much bigger space, in other words, on tensors, just as directional covariant derivative along a certain direction is. And it's linear, not in the thing that it acts on, that's part of the definition of derivation, but it's linear in V, in the argument V. Okay. So in other words, Lie derivative with respect to the sum of two vector fields is the sum of the Lie derivatives with respect to the individual vector fields. Second of all, the Lie derivative of a scalar, this we just saw, is equal to VA grad A phi, grad A phi, which is, of course, can be written. That's the first formula we had. And here's a very important one that I won't prove because so what does this mean? This means that if we apply the Lie derivative and we apply the gradient, to the gradient of a scalar field, it's the same thing as taking the gradient of the Lie derivative applied, which is just the directional derivative in that case, of the scalar field. Now, I won't prove that because if you think about it the right way, I mean, you can, of course, we have some formulas for these. So you can, of course, plug into those formulas and check whether it's true. But it's more educational to convince yourself that it's obvious. And if you can convince yourself that it's obvious, then you understand the notion of the Lie derivative. You understand in what sense the Lie derivative is an infinitesimal diffeomorphism, and you understand something about general covariance. So how can I make it seem obvious? The point is that, so imagine taking I don't know if I can, well, let me give it a try. So imagine taking a scalar field and converting it to the, taking its gradient. And now let me take some sort of Lie derivative, which I'll just represent by this C. Well, I've been calling it V, so I'll keep it as V. And so I'll get sort of phi minus Lie derivative of V along phi along V, and here I'll get something. So what this represents is dragging this by the vector field V. But dragging by the vector field V is just a mapping of the manifold itself, right? If I go to any point and I go a parameter distance t along the vector field that's sitting there, that just gives me a map. Well, maybe I'll say something a little more about it now, actually. Yeah. So I'll try and write a few formulas in a second. So let me just say it in words now. So that's just a diffeomorphism. The Lie derivative is just dragging an infinitesimal amount along the vector field V. And so that's an infinitesimal diffeomorphism. So what I'm really using here is I won't write out the thing. It looks a little bit too messy, but it's just the gradient. Well, here, this way I can write it. It's the gradient of phi minus V. What I'm really using to make this obvious is not something about infinitesimal diffeomorphisms, but it's something that's true for any diffeomorphism. If I take a diffeomorphism, if I apply a diffeomorphism to the gradient of some scalar field, I'm going to get the gradient of the scalar field that the original one was mapped into by the diffeomorphism. And the way to think about it is that this thing, it's to think what underlying structure, what physical fields, if you like, or physical object do I need in order to take this gradient? And in the case of a differentiable manifold, we don't need anything except the differentiable structure of the manifold itself. So this, it relies only on, I'll just write on M. By this I mean M is a differentiable manifold. Once you have that differentiable structure, then you know how to define uniquely the gradient operator. But a diffeomorphism is by definition something that preserves that differentiable structure, and therefore it can't change the gradient operator. Because the gradient operator is built from, or it emerges automatically from the differentiable structure. So I don't know how, looking around, I don't think I've convinced too many people. But I claim, try, if you can convince yourself, this kind of thing, it's much easier to convince yourself than to have someone be able, than to put it into words for someone else. But once you do convince yourself, then you'll understand something very basic about the meaning of general covariance in differentiable structures. Yeah. Yeah. You mean if I actually had to compute calculationally? That's a good question. If I don't know if it'll be, I don't know, actually. I don't immediately see, but yeah, it might be. It might be pretty close. If I, yeah, it probably is. Actually, if I work with these, it probably will be. Yeah. Another question?
You run into a problem with these statements if an integral term of the vector field B ran into a singularity? You're trying to drag into something that's not there.
Right. So it's true that given a vector field V, I can't necessarily follow it forever for an arbitrary distance of, an arbitrary parameter distance. And that whether you can or cannot depends on the particular vector field. But in finite dimensions, for a smooth vector field, you can always follow it in a neighborhood of a point. You can always follow it for at least some finite parameter distance. That's enough to define the Lie derivative and to make these arguments. But you're quite right. It's not true. It's not in general true that the vector field can be integrated forever. If I were to assume, enough regularity conditions, then it could. But that's right. So for example, if I had a manifold, if this was my manifold, was just say Minkowski space, but then I decided, well, I'm going to cut a hole out of it, and my vector field was the time-like constant vector field. Obviously, I couldn't follow this for any finite distance because there'd always be some point that would run off the manifold in that finite distance. But on the other hand, if I just say, look in some neighborhood of some point, every point there could be followed for a finite distance, but finite parameter distance. But if I wanted to actually produce a one-parameter family of diffeomorphisms of this manifold from the vector field, then I'd better have the vector field vanish on this boundary where I cut out the point. If it did, then I'd be okay. I wouldn't be led off the manifold. But you're right, there certainly are global conditions on when you can integrate vector fields. Those come up a lot. I mean, something very closely connected comes up in the case of renormalization group, where there are these things called Landau pole. I don't know if you ever heard of it. It's a sickness of the lambda phi 4 theory, the self-interacting scalar field. And basically, what it's telling you is that the renormalization group flow, which tells you how the coupling constant changes as you go down in scale, go down into higher energies and shorter distances, tells you that it actually, so that represents a vector field in some space of coupling constants. In this case, I'm just talking about one coupling constant, but there's actually two, the mass squared. You have some sort of vector field in that space of coupling constants, and what you find out is that in a finite parameter distance, it runs off to infinity. And that's why, and then therefore the theory has no continuum limit. There's some smallest scale to which you can follow things and have a meaningful theory. So, yeah. So it comes. So examples where the vector field cannot be integrated actually have they're important in physics and have sometimes an important physical significance. Okay. So anyways, I'll say this is obvious. And then once you have that, then we can sort of compute, it makes it easy to compute the Lie derivative of a covector, because let's just take, at least it's easy to motivate the formula, simply, let's just take this covector to be the gradient of some scalar field, and then use this commuting, and then we can work out from that a formula for the Lie derivative of the covector field. And let's see what it I will just tell you what it is. I've called this omega A plus, now what do I want? Grad A dV omega B. So let's say compare with the fact that dV grad A pi is grad A dV. So in the case where where omega has this simple form, this formula gives us now a way of I would then replace this by the covariant derivative, and this I'll replace by what it is, right? And expand it out, and we'll see that you get exactly this formula, which is actually using that it's a derivation, and so it's actually more general than just being. And this is only a very special covector field, which is a gradient of something. But once you have it for that, then it follows for everything else. So the important thing is that you have this formula. So how can you remember this formula? It's very much like the rules for remembering the formula for how the Christoffel symbol enters into the covariant derivatives of tensors. In this case, there's no Christoffel symbol. Everything involved is a vector or tensor. So the covariant. So what this is telling you is that the Lie derivative of omega along v is just the directional derivative of omega along v, where we interpret directional derivative in this covariant sense, with a correction term. And as in the case of the Christoffel symbols, the correction term is purely algebraic. In other words, just something doesn't involve any derivatives of omega. And now, so to remember this, you have to remember two things. You have to remember where the indices go. But actually, if you look closely, there's nothing to remember because there's no other way the indices could go. You have to get a free index A, and it's not going to be on omega. Then that would be a trivial. Then you would just have some multiple of omega. So once it's not an omega, it's got to be here because it has to be covariant. And then the other two indices have to be contracted, and so it goes like this. So the only thing that you really have to remember is the sign. And unfortunately, the way the definitions are made, the signs are exactly the opposite of each other between the Lie derivative and the expression for the covariant derivative in terms of Christoffel symbols. So where you would have written a plus Christoffel symbol, write a minus gradient of v. And vice versa. But aside from remembering that funny sign switch, then all the formulas look strictly analogous. So let's take an, yeah.
This bit there.
This bit here?
Yeah, it doesn't work at curl.
Is a curl? Well, curl is a concept that doesn't exist in general. No. So curl is a very special concept that exists only in 3 dimensions. Well, I'm sorry, there is something called that we could call curl that generalizes this, but what it does is it takes a 0 form into a 1 form, if you know that language, which is what's happening here. Then it takes a 1 form into a 2 form and a 2 form into a 3 form. It's also called exterior derivative. That's a kind of generalization of a curl, but it takes you from one type of tensor to another type of tensor. If you want the curl of a vector field, that's only something that exists in 3 dimensions with respect to a particular epsilon. I'm not sure if I'm getting to your...
What I was getting at was that you wrote W as a gradient of a scalar. Can you do that?
It's not... I thought I said that you can't always write omega as a gradient. This is meant to be an omega. It's not very legible. So you cannot always do that. That's right. So what in general, This, I meant omega A. So this is a very special one because its curl is 0. That's what you're getting at. So only if omega has 0 curl or exterior derivative can it be written like this, and then only locally in general. But that, I'm just saying this is consistent with this. The most general one, I would have to take, I'd have to multiply this by another scalar, and then I have to take a sum of a couple of terms, or depending on what dimension I'm in, a few terms of this nature, and that would be the most general. Then I could apply it to that. Or the other way of doing it that's sort of more straightforward, but this is just the simplest calculation I could have written down. But the other way of doing it is just to use the fact that Lie derivative commutes with contraction, which I don't even know if I actually wrote that down, but maybe I should. Lie derivative commutes with contraction. That's what I see. I didn't write it because that's part of the definition of a derivation. So I didn't have to say that. So it's a derivation, maybe I should have said, on the tensor algebra, on the full total. So part of the definition of the tensor algebra is the contraction operation. Then in other words, then you write Lie derivative with respect to V of WA of this notation. Let's call it UA. So it's clear it's not the same as omega. That should equal Lie derivative of U contracted into omega plus U contracted with the Lie derivative of omega, right? That's being a derivation. Once you have that, then it tells you what the Lie derivative, and this has to be true for arbitrary U and arbitrary omega. And since we know we have a formula for this, we can work out what's the formula for Lie derivative of omega. That's sort of the more straightforward way of getting it. That's in effect what we did for the Christoffel symbol expressions in covariant derivatives, I think. I may have got it another way, I don't remember exactly how. Okay, so then there's a formula, I guess, for the, if people can see, maybe they can't see. Write the one last formula, which is the Lie derivative of a tensor. So it'll have many indices like A, B, C, D, and that'll be the. I'm just sort of reminding you what the rules are for tensors once you have them for vectors and covectors. So it'll just be, again, the directional derivative, covariant derivative, plus correction terms, and there'll be one term for each index on T. And each term will look either like this. Oops. Maybe I didn't actually say that. Where was our formula for the? Yeah, here's the formula. So I didn't actually point that out. So the Lie derivative of a vector as opposed to a covector, it's the directional covariant derivative. And then this we now can view as the correction term. The correction term again is algebraic in W. It involves the gradient of V. The indices are in the only way that they can be, and the sign is minus. So it'll be either a correction term of this nature, or it'll be this correction term here, which has the plus sign. And as I said, the signs are opposite. Opposite to the things that you're used to from the Christoffel symbol. Okay. Any questions on those? More questions? So now, I wanted to go back to this interpretation of the Lie derivative as an infinitesimal diffeomorphism and connect that up with the notion of killing vector. So, as I said, a couple of times, we can imagine this vector field. So I've switched over to this C here. No, I haven't, but I will in a second. So this is like an infinitesimal diffeomorphism along Xi, or might say generated by Xi. So imagine Xi is going like this, as always. And we want, as I said, you want to take the derivative of some other field, say a tensor field. Taking the derivative means to take its value here and compare it, subtract off the value here, which we can do either by moving the value here to the tip, or taking the value at the tip of the vector and moving it back to the tail. So before I did it the first way, now let's consider the second way. So this means make everything flow backward along the vector field C and just sit at this point P and watch how the thing changes. And so the Lie derivative of some tensor T is just equal to partial T over partial T, where this T is this fictitious time, and this T is the result, the flowing T. Yeah. So in that sense, it's an infinitesimal diffeomorphism. It's just if we think of the definition of this derivative, we just take T of, we just think of T of 0, T of T minus T of 0 over T or something. Think of T as going to 0. That becomes then an infinitesimal diffeomorphism. So you're asking, how does the tensor field T transform or change under an infinitesimal diffeomorphism? Therefore, and the rule to transform it, here I pulled it backward, so the rule to transform it forward is T goes to T minus some epsilon times leak C of T. Right? This is forward, this is pushing, or the other one was pulling. Okay. So if we take any fields T, in fact, they don't even have to be really tensor fields, but let's take any tensor fields T, and I apply this rule, the Lie derivative will always make sense, because as long as it makes sense to apply a diffeomorphism to whatever kind of object it is. I could even apply this diffeomorphism to the connection itself, which is not a tensor, but I'd still get a well-defined Lie derivative, which would be a tensor. So, because that is just an infinitesimal diffeomorphism, from a physical point of view, it's pure gauge. If we apply it to everything, right? So if we apply it to the metric and the electromagnetic field and the particle world lines or whatever may be present to describe the physics, if we apply that diffeomorphism to everything, that's pure gauge. That's just the restatement of general covariance. So if we apply an infinitesimal diffeomorphism, that's also a gauge transformation. But it's just sort of to first order a gauge transformation. And that'll show up at some point, if and when we get to it, it'll show up in dealing with gravitational waves, where you describe them by a small linearized perturbation to the flat metric, but you notice that it looks that linearized perturbation looks like a gauge field, and the gauge transformation is precisely the one induced by an arbitrary vector field. And we'll see and basically it's the Lie derivative of the metric along that of the Minkowski flat metric along that arbitrary vector field. So we'll see the formula. We won't do the gravitational waves now, but we'll see the formula for it. Oh, the other general thing that I wanted to say, again, this is obvious, is that I think I almost said it before, is that the Lie derivative along some coordinate, let's choose a coordinate chart, and then a basis vector of that coordinate chart, and take the Lie derivative along that basis vector. In the coordinate chart, that goes over to just partial x alpha. Okay, it's obvious if you believe everything else I said before, because we're just asking how do things change under the diffeomorphism generated by the vector field. But in the coordinate system, this vector field, the coordinate basis vector, is just the constant vector along some direction. And so to drag everything by it is along that vector field is just to translate everything to a different coordinate value, and that otherwise nothing. Well, that's the diffeomorphism in question, and that diffeomorphism, under that diffeomorphism, the components don't change; they just move around. The tensor components just move to the new location. So what it means, if you believe that, is again, this is one of these obvious things. Not quite as obvious as the other one, I would say, but it's obvious in a similar sense, is that this Lie derivative in the coordinate basis direction of any tensor field equals 0 if and only if in the chart T, is independent of x alpha. In other words, its components are independent of x alpha. So this will be important in practice. This is usually how it will look. If you can find a vector field, if you can find a coordinate system in which the components of some tensor are independent of some coordinate, typically it will be time or angle or something like that. So let's say time. If you can find a coordinate system in which the components of the metric are independent of time, then it means that you can find a vector field, which is just the d by dt direction, the E0 vector field in that coordinate system, with respect to which the Lie derivative of the metric vanishes in that case, or more generally the tensor. Okay, is it clear? And conversely, if the Lie derivative vanishes with respect to some vector field, then it means you can always choose the coordinates so that that vector field becomes one of the coordinate directions, and then you'll get that the object whose Lie derivative vanished has constant components in that coordinate system. Now, given that, let's talk about killing vector. What's killing vector, which really should be called killing vector field, is an infinitesimal isometry. So remember what an isometry is a special case of a diffeomorphism. It's a diffeomorphism that preserves all lengths and angles, or in other words, it's a diffeomorphism that preserves the metric. An infinitesimal diffeomorphism is a Lie derivative along some vector field. In the case of an infinitesimal isometry, we call that vector field a killing vector. So we say that C is a killing vector if and only if the lead derivative of the metric with respect to that is 0. So that's the definition of killing vector. If we write out what that means, let's write out what is, using these rules now, what is the lead derivative of the metric in general. So it'll have 3 terms, right? It'll have CA, oops, let's call it C, grad C, GAB. That's the derivative term that's always there. And then, because then there'll be 2 correction terms, one coming from each index. And because it's a because it's a covariant tensor, they'll be occurring with plus signs, and it'll be, so what do we get? And they'll both take the same form. They'll both involve the gradient of the vector field. I switched to C because that's somehow the more traditional one in the context of killing vector. I'll take the gradient of the vector field that's in the argument of the lead derivative. I mean, that's whatever you call this. It sits here underneath the lead derivative symbol. Take that, then we have to contract. So we have to then act on each index. So if we let the active index be A, so that has to be contracted with something, and the only thing it can be contracted with is this. B is just going along for the ride, and then I have to have, I could call it C, I suppose. Well, anyway, maybe I should just call it C. And then for uniformity, and then I have the active index is sitting here on the gradient operator. And then, well, this is symmetric. I mean, then I do the same thing on the second index, make B the active index, and let A just be the bystander index. So it's just switching A and B. So I'll get B here, grad C, GA, C, right? Okay, so this is just the application of this formula that disappeared. Did it disappear? No, here's the formula. It's the application of this formula to a tensor now, which is a rank 2 tensor. But of course now, so this is true for any rank 2 tensor whatsoever. Doesn't need to be symmetric or anything. But now, of course, if it's the metric, then by definition, this thing is 0. And furthermore, since it's the metric, since I can pull the metric tensor inside for the same reason. I can pull it inside the covariant derivative. And so I just get grad A, G, this is not G, this is what we call lowering the index on C, right? So it's grad A, C, B, and then this is grad B, CA. So the case is, in the case of the metric specifically, and the covariant derivative matched to the metric, this is the formula for the covariant derivative of the metric. And then the statement that it's a killing vector is just sometimes called Killing's equation, is just that this thing vanished. That's Killing's equation. If you find such a solution, if you find any space-time and you find a solution of this equation, then you have an infinitesimal symmetry, an infinitesimal isometry of the metric. And then if you can integrate that up, assuming we don't run into troubles integrating it up, then you have a finite symmetry. So you have a translation symmetry along this vector field. And if this is a time-like vector field, then we would call it a time translation symmetry or an invariance. So basically we have what's called a stationary vector field. So a stationary metric, sorry. So if CA is time-like killing vector, then we say that GAB is stationary. Sometimes you say it even with respect to other directions, but especially in the case of time-like vector field, you say it's stationary because it's not changing with time. If you make this be the definition of time. In that case, you can always choose, just as a special case of what I always said before, you can always choose coordinates such that the components G alpha beta, I'll just write it like this, they're not functions of t, meaning they're independent of t, right? They may depend on x, y, z, r, theta, phi, or something, spatial coordinates, but whatever other coordinates you introduce, but they won't depend on the time coordinate. So conversely, saying that there's a time-like killing vector is, to some extent, just a fancy way of saying that you can choose these kind of coordinates. But as usual, it's more general because you're not generally able globally to choose coordinates. And then a small caveat, not a caveat, I don't know what to call it, but it's not a caveat, it's a warning or something. It's that the word stationary has a special meaning in relativity. That it's not the same as what's called static. So if you say that this metric is static, the gravitational field is static, you're saying something a little stronger than just stationary. So I wanted to say a few general remarks. Maybe I've already said all of them, almost, but let me say them again. On the relation of gauge to Lie derivative. So the things I said before, but I'll try and make them a little more concrete now. So let's suppose we have some manifold, whatever it may be. And point x belonging to this manifold M. And we have some other manifold, which I'll call M bar. Some point x here. And I have some diffeo F, diffeomorphism, taking you from M to M bar, and it takes, say, the point x to the point x bar, I'll call it. So x bar. I'm just trying to give general covariance, I suppose, a more precise definition. And then I can have any geometric object in or on M goes under F to some other geometric object in M bar, because it's a diffeomorphism. So diffeomorphism means a one-to-one, really, one-to-one, map which between points of M and points of M bar, which is smooth in both directions. So I can always do that. And of course, what general covariance tells us is that these two situations, M with all these objects, whatever they may be, these fields and world lines and so on M, and this M bar with the corresponding fields and world lines on that, describe the same physics. That's the statement of general covariance. So let's take a couple of examples. How do you, of transferring fields from the one to the other. So one example, suppose I was dealing with a scalar field. So suppose I'm given it on M bar. So it's a map of N, say a real scalar field, a map of M bar into R. Then from that, I can derive a scalar field on M How? Well, this scalar field here was just a map from M bar into the real, so I just compose it with F. And I get a scalar field on F. Okay, so that's called pulling back the scalar field phi bar from M bar to M. What about a vector field? So vector field, so it's a vector field. So remember what a vector, so the vector fields actually go forward more naturally. It's easy to write the formula for them to go forward, push forward as it's called. So suppose that the vector field, suppose it was the equivalence class of some set of curves. Remember how we defined vector field, equivalence class of some set of curves. Then how do I get a vector field over here? Well, that's obvious. If I'm given a curve here, I just transfer it over to getting a curve here. So that means I have, let's call it V bar, just another bar on the index to show that it belongs to another manifold. Then that will be, of course, the equivalence class of F circle gamma. So you're always just composing things with this map F. That would be the vector field to which, or the vector to which V goes over, where this gamma was a map, was a curve in M, in this case, not an M bar. And we write this as V bar A bar equals, remember the notation we had for this. We used it in the case of a chart. Now I'm generalizing it. There's no charts here, but just two manifolds, two general manifolds. I use the same notation, F star A bar B bar B, A bar B, 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 right? Which we could introduce even a notation. But I didn't introduce this before, but we could. It looks confusing because this strongly suggests that you mean coordinates, but I don't mean coordinates. I just mean points x and x prime. Probably if I went back to the other notation, I should call this p bar and p. It's partial x bar, partial x, b, v, v. This is another notation. So this notation is very natural. It shows you exactly what's happening. And it has the usual virtue that it goes over exactly to the coordinate notation when you introduce coordinates. So this defines F star. In the case of, what about the case of a covector? So now there's some funny thing that the covectors naturally go backward and the vectors, contravariant tensors more generally go forward. You can, of course, go both ways because this is an invertible map, but it's easiest to write the map in one way or the other depending on whether it's a vector or covector. So let's take it to be omega A bar in the cotangent space to M bar. Then we can make that go to omega, which is omega bar circle what? Well, F star I need in this case, because I have to make it act on vectors, which that has another notation. It's written as F star of omega bar. And in coordinates, I mean, in this kind of coordinate, this notation that can be easily confused with coordinates, we would say omega bar. Oops, what is this? You would have say omega A. I should have put it like this. Partial x A. Okay. That would be using this notation. I mean, this is equal to so that's another notation for how F star acts. So that's generally called pullback. So the scalars, which I guess from this point of view looks more naturally like a covariant object than contravariant, and the covariant tensors are naturally pulled back, and the vectors and contravariant tensors are naturally pushed forward. So again, the Lie derivative is just the infinitesimal version of this activity in this. Whoops! Oh, I always get. I always look at that clock and think, oh, we have half an hour. Okay, so I see we don't. Okay, so the Lie derivative, the Lie derivative is just the infinitesimal version of this activity where M and M bar are the same manifold. Oh, that's too bad. Well, okay, it's a good stopping point. So next time, well, yeah, it's really late. Okay, I'll quit now. So next time we'll, yeah, that's all I need. Next time we'll start using this fact. So we've defined the main thing that the Lie derivative will let us do is define a notion of infinitesimal symmetry, or a notion of symmetry, as we've seen in an example of stationary. And you're used to the fact that whenever you have a symmetry, you have a conservation law, and that's what we'll do next time. We'll show how to derive. First of all, we'll write down an action principle for a particle that includes both massive and massless particles, so we can do light as well. And then we'll show by a very simple argument how the existence of a killing vector will result in a conserved quantity along the world line of that particle. Basically, yeah, and then we'll start applying that to the case of the Schwarzschild metric, where you get, because in the case of the Schwarzschild metric, you have actually, in some sense, three symmetries. There's the time it's like you imagine a star sitting here. It's independent of time, so there's a time translation invariance. There's a rotational symmetry, which is actually 3-parameter, but only one of them is needed for the orbits. And then there's this parameter lambda, which we'll have to talk about in the case of light, but there's an independence of the lambda also. So you actually have 3 symmetries, and that's enough. Or in the massive case, you have an extra condition. Well, you have that symmetry, and so you have the 3. That's enough to reduce the whole problem of motion to just a first-order differential equation, as you might be familiar with in the Newtonian case. So that'll be the application. But